Nicoletta Noccetti, and today she will present her work on Gray Code Kernels as a computationally efficient filters for video analysis. Whenever you're ready, Elena.
Thank you very much, Issa, for the introduction, and thank you to everyone attending the seminar. I'm Elena Nicora. I'm a third-year PhD student, and during these years, I've worked mainly on the understanding of motion information in video. In this seminar, I will talk about an efficient method for compute and to represent motion-related information in video. Biological perception, biological perceptive systems are able to understand a lot of visual information all at once because they have the ability to concentrate on a specific area or a specific object of the scene. And this relies to the definition of the saliency of an item that neuroscience defines as the state or quality by which this item stands out from its neighbors. And of course, this is related to the visual sensory systems, but also to all other sensory systems. In computer vision, this problem can be the problem of understanding of replicating visual saliency can be replicated into different problems in different tasks. And it can be based on the appearance of what we are seeing. So, for example, foreground detection and object segmentation base themselves on the spatial changes, on the appearance of the objects, and can be, of course, replicated to both in images and videos. What we are interested in mainly is to understand saliency, is to define saliency based on movement. So motion-based segmentation could be one of the tasks that computer vision uses to replicate this state. And one of the most used methods nowadays to applicate in computer vision is, of course, the use of deep learning. And when we are dealing with videos, maybe if you have enough data, you don't have to necessarily tell the architecture to concentrate, to focus on a specific area, because this information might be automatically learned by the method. But this is not something that is always possible. Of course, if you we are interested in real-time applications, if we care about portability, so if we have limited computational resource, traditional methods are still very much considered in the field of computer vision. But of course, saliency detection is something that is also used as a pre-step, a quick pre-step in inserted in a much more complex pipeline where the final goal could be something more high level. And we are, of course, concentrating on this last point. So we want to include a quick intermediate step in a complex pipeline. And while while studying the literature, we found this bank of filter that comes with also filtering scheme that is general enough to approximate any kind of filters, basically, and under specific circumstances can be used also as an highly efficient filter scheme. This is the family of the Gray Code Kernels, introduced in 2007, and this large family of filters, of course, is it includes also the well-known Walsh-Hadamard kernels. In literature, mainly are used as a pattern matching technique. Is used as a projection scheme to compute distances between patches mainly in the 2D domain. So in this slide, we have example of work about 2D pattern matching, motion estimation, and more generally on the optical flow estimation. That is the computation of differences in motion between images at pixel level. So all these work in literature are mainly, are quite exclusively focusing on 2D data. While we are interested, of course, in video, so in motion information, but why Gray Code kernels could be considered as a good ally in motion-related video tasks. So first of all, filtering is fundamental in several computer vision tasks. Their time and memory efficiency can be used in real-time scenarios and when computational resources are limited. Their generality can approximate any desired kernel, literature says that they particularly work well on natural images because they have a packing energy efficiency. So let's see what this efficiency is about. Basically, when using a set of such filters, successive convolution of an image will require only 2 operations per pixel for each filter, regardless the size of the kernel. So basically, if we have a set of filters, the convolution of given the result of the convolution of the first kernel with the image, the second convolution, the second result of the convolution can be obtained with only 2 summations per pixel. So basically, we don't have to replicate a complete convolution with all the kernels in the family. So of course, I know that most of you will know the definition of convolution. We can introduce the concept. Convolution is an operation that, for example, in image processing, sorry. It's an application of an operator to an image in which the ending result would be an image of the same dimension of the original image, but which pixel values would be the simple linear combination of the image pixel and the kernel values. In a classical spatial convolution that you can see here in the video, the number of operations needed would be linear to the image of, depending on the image, the dimension of the image, but also on the dimension of the kernel. So for each pixel of the image, we will have k by k operations. While in using the Gray Code kernel convolution, we will have only a fixed number of operation for each pixel, meaning that we will only depend on the dimension of the image.
Sorry,
so,
Elena. There is some kind of background noise. I don't know if someone in your room or
no,
you don't hear anything. Okay. Okay. And okay. Thanks. Anyway.
Let's see let's dive in deeper with this efficient filtering scheme. The main point is that the Gray Code kernel family can be created recursively with a binary tree. The efficiency depends on the ordering in which they are applied to an image, and this optimal ordering is linked to the definition of alpha index. So here we can see our binary tree. In order to create our filter family, we just need a seed S that would be our root, and a parameter k. K will indicate the number of levels in this binary tree, but also is linked to the final dimension of our filter families, and also to the number of total kernels that are in the family. As you can see, every node of the binary tree is composed by the father and the father depending on the label that is on the edge. So in this case here we have S concatenated with the S positive, and in this case we have S concatenated with minus S. Of the final kernels in our family would be the kernels that are at level K, so the leaves of our binary tree. Of course, here I will explain the composition of Gray Code kernels in one dimension because it's more intuitive, but I will show later how to expand to higher dimensions. So as I said before, it's created recursively. So every filter kernels that we find on the leaves of the binary tree is uniquely defined by its alpha index, and the alpha index is composed by the labels of the edges that goes from the root S to our leaves. So in this case, the alpha index of this kernel B1 would be plus plus plus. As I said before, the efficiency is based on the ordering in which we apply these filters to an image, and the optimal ordering is based to the definition of alpha index. In this case, the alpha index of B2 is plus minus plus, and the two filter kernels can be are considered alpha related if and only if the Hamming distance of their alpha indices is exactly 1. So in this case, the alpha indices of these two kernels differs only for one element. In this case, we have so B1 and B2 are alpha related, meaning that if we have the convolution of an image with B1, the result of the convolution with B2 can be obtained using only 2 operations per pixel, like here. The theorem that is behind this filtering, the core principle of this filtering scheme, is basically that 2 alpha-related filters share a common prefix of length delta. And if we compute their sum and their difference, we can see that this relation holds, meaning that every element at position I of their difference can be found exactly the same at position I minus delta in the vector of their sum. So if we expand the sum and the difference, we obtain this core principle here that is the base of our efficient convolution. And for linearity of the convolution, we can switch from the vectors to the signals resulting from convolving the image with the two kernels. So as I said before, the higher dimensional kernels can be generated by computing the inner product between one-dimensional kernels. So the binary tree that we saw before is the base for every type of kernel that we need, and also there is the alpha index of the higher dimensional kernels is the concatenation of the alpha indices of the one-dimensional kernels. So this means that all the rules that I said before apply also to higher dimensional kernels. Here we have an example for this two-dimensional kernel here. It's obtained by inner product of this one-dimensional kernel and this one-dimensional kernel. And of course, the alpha index would be the concatenation of this one, so plus plus and plus minus this one. Since we are interested in videos, the natural way was to switch to 3D Gray Code kernels. And the interesting fact is that after we computed them, we noticed that the resulting kernels within this family were able to highlight different type of information in the image. As you can see, the blue cubes here captures changes only along the x and y axis. So we will call them spatial filters, because we need to keep in mind that the z-axis is the one assigned to time. So in the same way, we have these green cubes here that capture changes only along the z-axis, so along the time components, and we will call them temporal filters, while the other capture changes along all three axes. So we will call them spatio-temporal filters. Needs to be said that when we are switching from one-dimensional to higher dimensions, even if we start from a series of one-dimensional filters that is alpha-related, this doesn't mean that the resulting higher dimensional kernels will be alpha-related successively. So we need to keep in mind that in order to apply the efficient filtering scheme, we need to rearrange the filters in the right ordering. So now I will show you how we decided to apply this filtering scheme, this 3D filtering scheme on videos. Since we have cubes that are related to the number of levels in the tree, we wanted to, and this is, and the dimension is 2 to the power of k. We wanted to use the same dimension of blocks of frames in a video. So we take a block of 2 at the power of k frames. We apply all the m filtering family, and we end up with m 3D representation for each block. we noticed that in these 3D representation that are a lot of data, basically the central slice of these cubes, of these representations, were able to compress, to collapse a global information about this block of frames just in one 2D representation. So we selected this central slice, ending up with a representation, 2D representation for each block in the video. So after applying the filtering video, we will end up with, for each pixel, a vector of values of the same length m of the family of kernel used. And this is one of the first things that we wanted to do is to look for to understand the global behavior of these filters. And we had this assumption that if nothing interesting is happening in some areas of the image, then it means that there are no events or particular situations that would trigger the response of a particular filter, meaning that all filters should behave more or less coherently. And one of the natural way to understand this global behavior is to compute the standard deviation of this vector of values. Here, since we can appreciate the fact that we had the division between spatial temporal and spatial temporal filters, we decided to compute the standard deviation of these values, considering only subsets of filters. And here you can see clearly the added value of adding time to our filters, because if the dark blue means that the standard deviation is close to 0, then we can see that the relevant part of the image is, so the subject that we are interested in is clearly highlighted in using the temporal and the spatio-temporal filters, while in the spatial only set of filters, we also have information about the appearance of the background, for example, and it's a little bit confusing, let's say. More in addition, here using here in the temporal, I don't know if it's visible enough. It seems that the background is not really uniform, let's say. This is because the temporal filters alone might capture problems related to the poor resolution of the videos if we don't have, for example, HD video, and problems related to white noise. So the best solution that we thought it could be selected was to analyze the standard deviation profiles for the spatio-temporal filters. Here we can see some examples. We selected 3 fundamental pixels, and we studied the standard deviation profile in time. We can see that in static points, like the body and the background, the standard deviation is more or less stable, while where the arms passes, we can see some kind of periodicity. Another interesting fact that can be highlighted principally here, we can see that we have also an idea on the starting and the ending of these events. So when this event is happening. This is the Weissman dataset, the dataset that I mainly worked on, and it's composed by 10 different human action at full body. This is another interesting dataset. Is mainly composed by clips of nature documentaries. And we can see that even in situations where it's hard to, even for the human eye, to capture motion, the standard deviation profiles of these filters succeed. Like in, for example, here where we have the yellow dot, actually there is a little bird falling, and this was not even captured in the ground truth, in the information about the data set. So, but the standard deviation is able to capture this. One last example is on the MaLGa dataset, a dataset that we acquired in collaboration with IIT, and is mainly focusing on upper body fine-grained action about cooking activities. Here we can appreciate the fact that in this action, the body is still. So it's the standard deviation profiles are similar to the point on the table, while here it's moving a little bit, and the movement is still captured by the standard deviation profiles. So at this point, we understood that a simple global analysis of these vectors of values, of projection values, could be able to highlight information about motion. Following the same intuition, we decided to compute the maximum of this set of values. As we can see, we have here we can understand where is where the motion is occurring in the maximum way, so the difference is higher. At the same time, we decided to compute also the average, and the very interesting aspect of these average pooling maps is that, of course, our projection values were normalized between 0 and 1, so we can expect values around 0.5. The interesting thing is that we have local minima and local maxima in a way, positioned in a way that we have some sort of information about also the direction of motion, as you can see clearly in, for example, in the first example. So at this point, in these cases, we knew that with a couple of simple computation, that is the filtering and a very fast post-processing of the values, we were able to highlight the position of where in the scene motion was occurring, the direction of the motion, so have an idea about the path that is followed by the subject, and also some sort of information about the detection in terms of beginning and ending time. But of course, this is not the case for some complex scenarios that in which this simple analysis is not enough. And I'm talking about cases in which we track subject with our camera, so the amount of movement of the camera is similar to the amount of movement of the subject, and you can see here that the subject is not clearly highlighted because it's immersed in a lot of information. Another example could be severe motion blur, and here we can see motion blur both in the background and in the legs of the girl, and also when there is background motion faster than foreground motion. So this general analysis is able to highlight motion in general. We can see in this last example that the information about the subject in which we are interested in is there, but is immersed in a lot of, let's say, noise. So since we have this way of highlighting the motion, so we have all these kind of information of motion, we thought that we can quickly identify this region of interest where motion is occurring. And saliency detection is not a trivial task. Is used in different formulation, and often the computer vision perspective on saliency is blurred, so we don't have a clear definition. Even if we have a lot of different formulation, literature at the end of the day will end up with often with binary segmentation, so with binary mask, in which we have an image telling us where is the salient object in a pixel level, at a pixel level accuracy. So how can we achieve this these binary maps? Simply by taking our maps, flattening the values, fitting a normal distribution, and finding a threshold to binarize the data that we have. These are some examples, taking the three maps that I showed you before. And of course, our 3D implementation, in the way that we applied it to blocks of frames, it collapses information. So it collapses information into a single image. And so the segmentation that we end up having is more related to a motion history image than an instantaneous segmentation. For this reason, we are not, of course, not able to compete in literature that uses pixel level segmentation mask. But at the same time, we are able to highlight the right region to look for. So we are, in terms of a region of interest, we are able to highlight the right one, and so we have the important thing is that we achieve this pretty reasonable result in a very short time, especially with respect to the literature. Here we can see some examples. So our segmentation is not really wrong, let's say. It's a little bit more broad than the instantaneous segmentation. So at this point, we were ready to take a step further um, into the computer vision task, in motion understanding task. And one of the most popular is, of course, action classification. So is our representation able to not only identify motion, but is representative power is enough to also classify actions, so distinguish actions one from the other. And to pursue this problem, we decided to focus on two completely different methods. One is more classical, using a bag of words approach, in which we use the saliency detection in order to highlight one of the area of the image, and then using the vector of projection values as feature vectors. And then we wanted also to switch to the deep learning based methods and see if these projections were able to boost accuracy or efficiency in deep architectures. A bag of words representation is based on the creation of a vocabulary of common feature vectors in order to represent in a more general way all the data samples. And this is how we formulated our approach. We computed the projections, and we used our projections to segment the salient part of the image. So instead of using all the pixel in the image, we focus on the segmentation, and we take the pixel inside the segmentation with their vector of projection values, and we use them in a clustering algorithm. From this clustering algorithm, we will select the centroids of each cluster as our vocabulary atom. And after that, we will translate all the interesting pixels, interesting feature vectors in histogram of frequencies of these vocabulary atoms. And we used, in the end, an SVM model. So these results are on the Weismann dataset. That is our first, for now, it's our first attempt in a Gray Code Kernel bag of visual words approach. The difference between the accuracy in this image, in these actions, could be related to the fact that the data set is composed by 5 actions that are performed statically, so in the same place by all the subjects, while the other 5 are performed going to one end of the scene to another. And the direction is random, is taken random from each subject. So the drop in the accuracy might be related to an unbalanced number of samples going from one direction to the other. So it might be biased on one direction specifically. This is, of course, a baseline, and this is how it is compared to the literature. And from the deep learning point of view, we wanted to test if, in a joint project with Vito Paolo Pastore and Matteo Moro, we are trying to test if our Gray Code kernel projections are able to boost the amount of information contained in the RGB frames, maybe helping in identifying faster the salient part of the image. For doing this, we used an Inception 3D model pre-trained on kinetics, and instead of using an RGB input, we decided to use the spatio-temporal Gray Code kernel filter responses. And in this first experiment, we saw that comparing the performances using only RGB and only Gray Code kernels, our accuracy was much higher than the baseline using only the RGB. Moreover, the representation learned by the first layers of the architecture is somehow related and consistent to the pooling to the pooling maps that we computed earlier. In the next experimental setup, we will want to change architecture to change to see if these results are consistent in using other data sets, and also we would like to see if RGB and Gray Code kernel projections can be used in substitution to optical flow in a two-stream neural network. So in conclusion, Gray Code kernels gives you an efficient way of computing cascading convolutions of a set of kernels on an image, and using 3D Gray Code kernels, we were able to efficiently highlight the salient part of an image in order to quickly identify where motion is occurring in a scene. In addition to that, we also noticed that the Gray Code kernel projections were also able to gather information about the timing and the direction of motion. In future experiments, we are planning to exploit this time and memory efficiency and of course this representative power to apply this saliency detection method in the robotics field in collaboration with the conduct unit at IIT. I think that's it, and thank you for being here.
Thank you, Elena, for the talk. So I think we're ready to take questions. So let me start by one then. How do you think this let's say fusion with the deep learning method is going to affect the inference time of and how the Gray Code kernels will help in reducing the let's say the computational cost of a regular deep learning framework?
Well, of course, Gray Code kernels have already been used to in a sort of to estimate the optical flow, and optical flow is something that is very much used still, but is very computationally heavy. So if we manage to reach some sort of similar results to optical flow without having to compute it, so using the Gray Code efficient filtering scheme, I think would be a boost to the computational power and the time complexity. Of course, they've been used on only on examples in 2 images, so we didn't really explore the use of 3D Gray Code kernels in the estimation of optical flow, but it's in our to-do list.
Thank you.
Thank you.
Any other question? Okay, so there seem to be no questions. I would thank you again for the talk, and thank you all for listening. Wait.
Yeah, sorry, it's not because I was trying to talk, but I realized I was mute. I just have one last question for Elena, if it's possible, because I haven't seen the bag of words results, So, but do you think, because I'm trying to understand, do you think that maybe the deep learning could be more, let's say, more able to generalize with respect to the bag of words? Because I was thinking, like, if the action if we are seeing the same action, but maybe, in a different way, maybe just the opposite direction, should it be, I mean, is my intuition correct? Like the bag of words would be sensitive to this?
Yes, I think so. I think that the classical bag of words method is too simple to generalize enough with respect to, for example, the direction of movement. Even if, for example, the same movement is computed in the same exact way by the same person. So I think it's a limit of the bag of words approach. Yes. So the deep learning method should be able to generalize.
Okay. Thank you.
Thank you.
Okay. Thank you all for attending, and thank you again, Elena. See you next week. Bye-bye.
Thank you.
Bye-bye. Thank you.